title of my presentation today will be on the absolute stable difference scheme for third order delay partial differential equation. We've worked on several problems involving delay partial differential equation, whereby in some problems we did look at problem involving involution and also problem involving Newman boundary condition and others. But for today, this is a work that we have worked on, me together with Professor Evren and also Professor Alebaran Ashralif on the absolute stable difference scheme for third order partial delay differential equation. So I will go over the abstract of this publication. For the abstract, we say that the initial value problem for third order, for third order delay differential equation in a Hilbert space with an unbounded operator is investigated. And then the absolute stable three-step difference scheme of first order of accuracy is also constructed, and we also proceed to analyze it. Also, the difference scheme is built on the Taylor's decomposition method of 3 and 2 points. And then we proceed to show the theorem on the stability is also presented. That is, the theorem on the stability of the difference scheme is proved. Also, in practice, stability estimate for the solution of three-step difference scheme for different types of delay differential equation are also obtained. Then finally, in order to ensure the coincidence between experimental and theoretical result, and also to clarify how efficient the proposed scheme is, we will see some numerical experimentation, some numerical experiment which will be tested. Okay, so as we know definitely that there are various problems in mathematics and the elasticity theorem, such as the problem of longitude oscillation and non-uniform viscosity rod, the problem of longitude impact of a perfect rigid body, and on non-uniform finite length viscoelastic rod with a variable cross-section, problem of waves, and so on have been investigated using delay differential equation. So in my talk, I will proceed immediately to focus on what we will be looking at for today. So we know that several physical methods led to initial boundary value problem for third order partial delay differential equations. It is known that such type of problem can be replaced with the initial value problem of third order delay differential equation in a Hilbert space. As we can see from equation 1, in a Hilbert space H with unbounded operator A, here B will be from element of R1, and we will also assume that f of t is a continuous function on the interval from 0 to infinity, and also f of t will belong to the following domain as being described, and also g of t is twice continuous differentiable function on the following interval. Okay, so first of all, we would like to give the main theorem of a particular paper which is being referenced here. So from theorem 1, the solution of problem 1, that is the problem above which we have here, satisfies the stability estimate. As we can see, the stability estimate given from equation 1, as well as that given in equation 2. And A naught is being defined to satisfy the following condition. Also, in general, AN for n taking values from 1 to 3 above will also satisfy the following max function that has been defined over here. So in practice, stability estimate for solution of several problems of third order PDEs were obtained. So let's proceed a bit so that we look at how we will be able to make this presentation based on what we have. So the construction and investigation of stable difference scheme for approximate solution of third order PDEs is of great importance, as we know. So our main aim is for us to construct the absolute stable three-step difference scheme of the first order of accuracy of the third order partial differential equation for the approximate solution of the problem that we present earlier above here, that is problem 1, the equation 1 that we have above here. Good. So we will construct the following uniform grid points. So here, the following uniform grid points here is constructed because it is what we will need in order to work for the approximate solution of the above problem, which we showed, where tau here is greater than 0. So if we apply Taylor's decomposition method on 3 and 2-step points, and here we give a reference, where we can discuss, where you can see more on Taylor's decomposition. So if we apply it, we present the different scheme of first order of accuracy. So for equation 1, by applying the Taylor decomposition method on 2 and 3-step points, we will be able to obtain the following first order of accuracy, which we can see here presented in this system 4. So for the approximate solution of problem 1. So the organization, as we will see in the first, we will have to present the second section of this will be the presentation of the stability of the different scheme, which is 4 here. We'll present the stability. And in the third section, the stability estimate of different scheme for the approximate solution of 3 problems for third order PDEs will be obtained. Also, lastly, we will also look at the numerical solution, which we will provide for 1 and 2-dimensional third order PDE. That will come in section 4. And section 5 is just the conclusion of all what we've seen here. So as section 2, as we pointed out, our goal is that the main theorem on stability of this problem here, that is problem 4, this first order of accuracy, that is what we will now look into. So all over the following presentation, which we will do, first we will assume that H is a Hilbert space and A is a self-adjoint positive definite operator as defined as follows. We can see we define our R and also we define our R bar to be as follows. So now the 3-step difference scheme can obviously be rewritten as the system of a single step and 2-step delay system. So what we did here is just this system 4 that we've seen above here. So we now rewrite it as the system of single step and 2-step delay difference scheme, which we can see here in system 5 here. So for the solution of the DS, which we have here, applying, so here, if we apply 5, we can obtain the formula for the solution of the difference scheme. In this case, we are talking about the difference scheme of 4. So for this, we will consider 2 cases. The first case we would like to consider, we will take the case whereby 1 is less than equals to k, and also k is less than equal to n, and also we will consider for the interval where we have mn plus 1 is less than equals to k, and is less than equals to bracket mn plus 1 plus n. So m is taking the value as we stated here. It's just the set of positive integers from 1, 2, 3 above. So first of all, let's concentrate in the case whereby for 1 less than equals to k less than equals to n. So if we apply 5, we get the following difference scheme. So that will lead us to the following difference scheme, which is difference scheme 6. So therefore, we see that in this case, we are taking u naught to be equal to be defined as such, which will be defined as 7. And also by solving this, we'll have v naught to be defined as the following, which we will end up getting this equation 8. We'll end up getting equation 8, that is after substitution, making some simplification, we will end up with equation 7, as well as equation 8, where we have u naught and v naught, which happen to be kind of initial condition in this case. So for now, we now have 6, and also we have 7 and 8. So if we apply 6 and 8, we will obtain UK, here we are generalizing. So UK, in this case, if we realize here we have just our U naught, and here we have system 6. So if we apply this U naught, we look at system 6. So that will lead us, after further simplification, we will obtain UK, and that is what we have as the following system. So by interchange of the order of summation, if we interchange the order of summation, that will lead us to having what? Equation 9. And this is for the solution of the differential system 4 that we presented earlier. So in the next case is that we are considering the case whereby, that is the second case which we said, where 1 plus mn is less than equals to k, and we have k is less than equals to mn plus 1, considering the fact that m is set of positive integers from 1, 2, 3 above. So applying 5, we will get the following difference scheme. So now we have the following difference scheme in terms of difference scheme 10, which we have over here. So therefore, we see that in this case, after simplification, we'll obtain our u of k to be equal to the right-hand side, as we've seen here, which is equation 11. And also for that of, if we proceed, in this case, we realize that we obtain u naught. Let's don't forget here, we obtain only u naught and vk. But here, as we proceed after further simplification, we obtain v m of n, where n, we shouldn't forget that is integers, which takes the value from 1 to 3, set of positive integers from 1 above. So that leads us, after simplification, we will be able to obtain equation. We'll be able to obtain this equation 12 after further much simplification. So applying formulas 10 and 12, then we will obtain that uk will be simplified so that we have the following system that we are seen here. So if we proceed by interchanging the order of summation, we get the solution of the difference scheme 4, which we've seen earlier, and that leads us that UK, we simplify it, we obtain it as what? As 13. So this leads us, by interchanging of the order, we get the following solution. So this is the solution that we've been targeting. After the simplification that we present and substitution, it will lead us to the solution, which is UK that we are following. So also, we have some lemmas that are very important in what we are doing presently. So in this case, the following lemma will be needed in the subsequent part of this problem that we'll be seeing. We have equation 14, 15, as well as 16. These are some estimates which are very important, estimate regarding R and R bar, which we have here. So the proof of estimate 14 and 16, so which we have this case to 15 and 16. If we want to go through the proof, this is just straightforward. It is based on the spectral theory of a self-adjoint operator in a Hilbert space. If we want to read more about that from this, we can go to the reference which I gave here in 39. We will see much more about self-adjoint operator. So now let us study the stability of this difference scheme 4. So our goal now is for us to study the stability. So the solution of difference scheme 4, which we presented earlier, here we are saying that it satisfies the following stability estimate, that is, it satisfies estimate 17 as well as estimate 18 based on the condition that are given. So in order to prove this, let us estimate. Here we have B1 general, here we have Bm plus 1. So here it will start from B2, B3 above, and also here we have B naught. So if we want to estimate B1, we can use the formula 9, which we present earlier, and the estimate 14 and 16, which we just pointed out that they are very crucial in establishing this proof. If we try to use it, we simplify, that will lead us to the following inequality that we have over here. So it will lead us to having this inequality after much simplification, the following inequalities. So that is what we use to obtain the following inequalities. So from that, and the fact that if we take U naught to be equal to G naught, it follows that we will have the following inequality after substitution. It will lead to the inequality we have here 19 for the solution of the difference scheme 4. So all what we are doing today, we bear in mind that we are talking about the solution of the difference scheme of 4. That is what we are observing. So applying formula 6, 7, and 8, then we can now write our V naught to be the following. And if we simplify, we will see that it will give us the right-hand side of this equation. Similarly, for V1, we will have the following. And for Vk minus 1, also if we simplify, we will be able to have the following equations. So using this formula that we've seen above, which we obtain after simplification, This formula leads to estimate 14. Use this formula and the estimate 14 and 16. That is, by 14 to 16, I mean 14, 15, and 16, we will obtain the following. So this is something very important, that after simplification, we will be able to obtain this. So it's quite a bit of a long process. So combining this estimate, we will now obtain the following, which is equation 20 that we have here for the solution of the difference scheme 4. So the next is for us to apply formula 6, 7, and 8. Then if we do that, we can now write the following. So that will lead us to having the following equations. So we have this equation. If we substitute, we'll also have the whole of this equation that we have all over here. The first, which is this. The second, we substitute. The right-hand side will give us this. And also, if we proceed, we will obtain the following long equation that we have here. And in this case, this is for the case whereby k is between 2 to n minus 1. So on further using the formula and estimate 14 and to 16, that is 14, 15, and 16, if we simplify, that will lead us to obtain the following. Though there is quite a bit of a simplification that has to be done, substitution, simplification, we will be able to obtain equation 21 for the solution of the difference scheme 4. So now estimate 17 will follow, follows from estimate 19 up to 21. So from estimate 19, 20, 21, we use that. So now the next goal, we will follow a similar procedure. If we recall here, what we did, we look at that of B1. So for Bm plus 1, if we use formula 13 and estimate 14, 15, and 16, after much simplification, we will definitely lead to the following. So that will lead us to equation 22. After we make all this simplification, we can obtain this estimate. It will lead us to equation 22 for the solution of the difference scheme 4. So we now move further to apply formula 10, 11, and 12. If we do that, then now we can be able to write. Previously, we recall that we've written that of V naught, but in this case, we are writing Vm of n, where n, we recall that it's taking values from 1, 2, 3, 4 is the set of positive integers. So we will be able to have the following. So on proceeding also, we will have the next equation that I highlighted here. And also subsequently, we'll have that of Vk minus 1. So if we generalize, we will be able to have this. And let's don't forget that here we have the following conditions attached to it, which I highlighted. So the next is for us to use the formulas that we've seen, and also equation 14, 15, and 16. If we proceed, we will also be able to obtain the following. So we see that the equation that we have, equation 4, coupled together with the conditions that we have, with much simplification, it leads us to obtain a lot of important results. So if we combine the whole of this estimate, because quite all right, we've seen that today we've obtained several estimates based on the simplification that we did, and then we will have also a very beautiful equation 23 that we have over here. That's, we obtain it after combining the whole of this estimate as well as the conditions that we are given. So for the solution of the difference scheme 4, if we apply equation 10 to 12, we can also proceed to write the following equations, which I highlighted. To each of these equations, it takes quite a bit of a simplification. So though anyone who is in need of the paper, you can easily download it and go over this simplification in order for someone to, if one would like to go over the details of the proof. So using the formula, this formula above, coupled with equation 14, 15, and 16, we will definitely obtain the following estimate, which we have here below. So we have quite a lot of estimate in this case. So for the solution of the difference scheme 4, estimate 18 follows from 22, 23, and 24, and thus theorem 2, which we've seen, is proven. Note that applying theorem 2, we can obtain the stability estimate. So if we apply theorem 2, that will lead us to the following stability estimate here, which we denoted as 25 for the differential scheme, which of our interest, difference scheme 4, which we've been working out throughout the day. So next part, because we divide this presentation into 3 parts, we have the application. So in terms of the application, in this case, we note that the generality of this approach permits studying of a general class of delay partial differential equations. So here, we consider the application of theorem 2 for 3 types of problem. First is the mixed problem for one-dimensional delay partial differential equation with non-local condition. So we have, which is being presented by this system 26, it's studied, but we have under compatibility condition. So we have the problem 26 will have a unique solution for the given smooth curve. So here we have quite a number of conditions here that we have to put into consideration in order for us to apply problem 2. So the construction of the full discretization of problem 26, it's computed in 2 stages. In the first stage, we consider the uniform grid that we have here below, which I highlighted, and then with step, we take our h greater than 0. So we have the following, which we consider it to be in a Hilbert space of the grid function, which we presented as follows. It's defined on the following interval, which is equipped with the following norm, as we can see here. So let me highlight it. So it's equipped with the following norm. So if we let the following to be the second order difference operator defined by, here we have it as equation 27, acting in a space of grid function, which I highlighted, which satisfies the following condition. So it is well known that the following differential operator is a self-adjoint positive definite operator in L12H. So if we apply the operator to 26, if we apply the operator on the following system, which we shouldn't forget that is a system for mixed problem with one-dimensional PDE with non-local condition. That is what we are looking at there. So if we proceed to make that application, we can obtain the initial value problem for infinite system of 3rd order differential equation, which we represent here as this system 28. But in the second stage, we can use the differential system 4 for 28. If we apply it on 28, we will definitely obtain system 29. So for the third theorem is that the solution of the system we've been studying, in this case, we are focusing on what? The difference scheme, in this case 29, it obeyed the following stability estimate. So we have the following stability estimate where we have C1 to depend on the following conditions. So for the proof of this is quite a bit straightforward. So the proof of the differential scheme 29, it can be written, the differential scheme 29, that is the equation we have here above, we can write it in the following. Here I have highlighted it. So it can be written in the abstract form 30 in a Hilbert space with a self-adjoint positive operator defined as such. So here we have the following condition which is attached to it. So therefore the estimate of theorem 3 follows from estimate 25. So it is quite straightforward. If we apply estimate 25 together with the conditions, we will see that the proof will quite be very obvious. So second, we also have this, if we let it to be a unit cube in the m-dimensional Euclidean space. So we are now looking at a mixed problem, but for this case, we are focusing on Dirichlet condition. So let's don't forget, in the other case, we didn't focus on the Dirichlet condition, but now we are looking at the Dirichlet condition. So if we follow the same procedure, as we can see, due to time factor, let me move a bit faster. If we follow the same condition, we will see that yes, the proof also it's quite very obvious, just as we did in the case 3, theorem 4. So all of them applying the discretization and the condition we have, we will be able to establish theorem 3, theorem 4, as well as theorem 5. But we know that most of the difference we focus, if we look at the boundary condition, we have a variety of boundary condition. In the other case, clearly we have here, if we move back a little, we see that the boundary condition we have here is Dirichlet. And for the other case, which we started initially, if we look at the boundary condition also, we will see that we are focusing on just a non-local condition in this case. So theorem 5 also, moving in the same procedure, we will be able to establish that of theorem 5, which is the solution of a difference elliptic problem. So we will be able to establish that. Here we are looking at a Newman boundary condition. So due to time factor, I'll be moving a bit faster so that we look at the numerical result. So in the case of the numerical result, in this case, we did look at a one-dimensional problem, and also we consider a two-dimensional problem. So let's take this case whereby here we consider the mixed problem, which has the exact solution of exponential minus t cos t. So here we have this mixed problem, which we represented for system 38. So for the one-dimensional delay partial differential equation, if we apply the system 4, if we recall, then we will get the following difference scheme. So we apply that will lead us to difference scheme 39. So this is quite a very good application of 4. So it can be written as the second order difference problem with the following metric. So 39 here, we just write it here as a second order difference problem with the following matrix coefficient. So here we proceeded to get the matrix, each what we have here, A, B, C, D, as well as the orders. So here we have a representation of U of S. We have a representation of A, which equal to C. We also have B written in form of a matrix. And here we have all of this, just the variable we have here, A, B, and C. These are the definition that we have. And also in this case, the following matrix also, we have it to be that. So if we put all of this together, it will lead us back to having system 39. Here we just write it in a matrix coefficient form, that we just write it. We get the matrix coefficient. So to solve the second order difference problem, we use the following formula in this case. So we have this is what we are going to use. And the goal here is for us to use a computer program such as MATLAB. We will be able to compute this. So using MATLAB to write up this system, where if someone is in need of the code that was used to write this, you can easily make a request of it, which I will be very glad to forward to you so that you can go over the codes to be able to replicate the same results that we get. So after using that, so we were able to compute the following error. So this is the table, the error of difference scheme, that is for difference scheme 39, which is a one-dimensional case. So this was the error that we obtained, whereby we have M and N, we have it to be 20, we have both to be 40s, and we have both to be 80s. So this is what we obtained. Also, when we proceeded for the two-dimensional problem, which we focused on the mixed problem with the Dirichlet condition, so we followed a similar procedure in that case, though we have the exact solution of the problem above here, 44, to be ut of x to be equal to exponential minus t sine x sine y. So if we apply the difference scheme that we developed to the problem which we have here, problem 44, the system 44, that is the mixed problem with the Dirichlet condition, we will be able to get the difference scheme of the first order of accuracy that we have here, which is system 45. So it can also be written as the second order difference problem with matrix coefficient 46. So here, A, B, C, D, we proceeded to write it in terms of a matrix, which we have it here. And also A, B, and C, we see that we wrote it in terms of the variables that we have. So in order for us to solve this, which we did solve using a MATLAB program, so we used the following equation 47, and we're able to write it in terms of a MATLAB code, which also I have the code with me for anyone who would like to move over to verify the following result, can request for that, which I will be glad to present to him to give to the person. So if we do that, we will have the following error of difference scheme 45. So what is quite interesting is that from the two tables we have, table 1 and table 2, we obtain the numerical result. And we see that in the case whereby if m and n are double, the value of the error decreases by a factor approximately half for differential scheme 39 as well as differential scheme 4.5. So we can observe that in this case, clearly we see for the first entry here, which I highlighted, we can see 0.0370. And in this case, we have 0.0162. And here also we see that 0.0083. So clearly we see that when we double the values, that is if m and n are double, the value of the error decreases by a factor of what? 1/2, that is half, 0.5, respectively, both for the system 39 as well as the system 45, respectively. So we see that in conclusion, from what we've seen, the absolute stable differential scheme of the first order of accuracy for the approximate solution of the PDE in a Hilbert space, which was presented, the theorem on the stability of this difference scheme also, which we're able to prove. In practice, stability estimate for the solution of three-step difference scheme for different type of delay partial differential equation were obtained, and also were able to present some numerical result. So for the second case, we see that the mixed problem for the one-dimensional delay partial differential equation having the Dirichlet's condition was stored. The first and second order of accuracy for the different schemes for the numerical solution of this problem were presented, and also we're able to see that the illustrative numerical result which we provided, we are interested in studying the absolute stable difference scheme of a higher order of accuracy of approximation, of approximate solution for the initial problem 1 for the delay partial differential equation in a Hilbert space. So what we are saying here is that here clearly we see that we focus on the first order of approximation. So this gives us the room for us to, anyone who will try to go on further investigation can decide also to say, okay, he will like to investigate the second order of accuracy as well as probably third order or so. But we can focus on second order of accuracy because here we focus mainly on the first order of accuracy, which is quite a very interesting thing that we would like to work on in terms of a future research. And if anyone who would like to also work together with us, we will be very, very happy so that we see that we are able to obtain similar result for second order of accuracy and much more other interesting case scenario. So I will be stopping here for my presentation.